Hello, my name is Ahmed Farooq, and I'm a researcher at Tampere Unit of Computer-Human Interaction. I'm working on designing and developing multimodal interaction systems for mobile, handheld, and wearable devices. Today, I'll be discussing our work on embedded haptic waveguides to improve tactile feedback. This research is a joint collaboration between Tampere University, Finland, Purdue University, USA, and McGill University, Canada. Current mobile devices use fibrotactile actuators to create artificial tactile signals throughout the entire device. Actuation mechanism is attached close to the rear shell of the device with limited focus on transmission. Feedback is never optimized for direct finger-based interaction. In fact, most of the actuation is delivered to the secondary hand or palm and not to the finger interacting with the touchscreen itself. Therefore, touchscreens events and haptic feedback are loosely connected, limiting information transfer rate. Most actuators are also not designed to simulate the skin receptors directly. In fact, their limited mechanical efficiency dictates how generic haptic feedback signals should be created throughout the entire device. In a haptically noisy environment, certain frequencies may be unusable, which may render this type of global haptic feedback system inefficient or weak. To circumvent noisy environments, higher frequencies may be utilized, which can cause unwanted results, such as erroneous selections or parasitic vibrations. Additionally, if we look at the interaction surface, which includes touchscreen displays and overlays, they also restrict the transfer of vibrotactile signals and cause attenuation and integration. Absorption and signal distortion at the point of contact is also rarely considered while designing haptic feedback for mobile devices. Therefore, signal from the actuator needs to be mediated to the point of interaction. Otherwise, signal filtration, transmission losses, and interference may render certain frequencies unusable or create dead zones throughout the device. For this reason, we propose the novel concept of haptic mediation, which is defined as a process of effectively relaying the actuation signal from the source, the actuator, to the necessary point of contact, the respective area of the skin, mitigating environmental noise and other internal and external inefficiencies within the system. Various adaptations of this technique have been documented in our earlier sensors publications. However, up till now, we've been able to use the haptic mediation concept through liquid mediation techniques only, which relay the actuation signal using specific liquids. Although this can be an efficient method for signal transfer, it requires mediation channel, a low viscosity liquid, to be present in the surface of interaction. To overcome this issue, liquid mediation, in this research, we propose a novel method of solid haptic mediation using 3D printed surfaces where the surface of interaction itself can act as a medium for relaying the applied haptic feedback signal from the source to the point of contact. To achieve this, we constructed multiple embedded haptic waveguides within the surface of interaction that can effectively mediate a specific range of applied signals. Existing research shows that there is a close correlation between the material properties of a waveguide, such as density, elasticity, and the resonance frequency of the system. In most cases, these properties remain fixed throughout the entire surface. However, within a 3D printed structure, it is possible to vary these properties by altering the fill rate and combining composite materials together, such as ABS or PLA. With this in mind, we created multiple waveguides within the 3D printed object by designing a 1.5 millimeter wide chamber or shaft-like indentation inside the surface itself, with a ratio of solid waveguides to empty space of 1:1. Here, the solid material acts as a waveguide, while the empty space provides an insulation around the waveguide, reducing the unwanted propagation of the applied signal. This technique reduces unnecessary energy dissipation and guides the applied signal from the actuation source to the point of contact. In our testing, we created various shapes and contours of the embedded haptic waveguides and tested their efficiency compared to the conventional 3D printed surfaces. Here you can see a comparison of an ABS material with and without embedded haptic waveguides across the frequency bandwidth of 80 to 220 Hertz, sampled at 90 millimeters from the actuation source. We can clearly see that the embedded haptic waveguide surface, shown in yellow, is more efficient at relaying the applied sinusoidal signal, displaying minimum signal integration and attenuation across the entire applied frequency bandwidth. To test this in a practical setup, we used 4 2mm thick overlay materials and placed them on a Microsoft Surface Pro device to compare the propagation of the same sinusoidal signal applied through a tectonic voice coil actuator. When we measured the maximum displacement and signal attenuation at the center of the device at about 95 millimeters away from the actuator for all the different overlays, which included Gorilla Glass, plexiglass, aluminum, and the 3D printed ABS material with embedded haptic waveguides. As expected, the results showed that the 3D printed material was more efficient at displaying the least amount of signal integration and attenuation. It also did not show any unwanted resonance or spikes within the propagation frequency. Interestingly, Gorilla Glass in red and aluminum in gray recorded the most amount of integration and attenuation. Results from the maximum displacements show that plexiglass and 3D printed overlay material performed quite similarly, with the latter achieving 19 micrometers of maximum displacement, but the former showing far more variability in the results. On the other hand, Gorilla Glass, the most commonly used overlay for touchscreen devices today, recorded the lowest displacement on average. We also collected results of a discrimination study, where the participants were asked to sense a single identical signal of 120 Hertz at 2 different points on the overlay surface and rate the perceived difference of the sampled signal. These points were 28 and 190 millimeters away respectively from the actuation source. Here we can see that the participants rated the 2 signals perceived at points A and B to be very similar with respect to intensity, distortion, and sensibility for the 3D printed surface of embedded haptic waveguides. Whereas the participants rated the perceived signal between points A and B for other surfaces, such as aluminum, Gorilla Glass, and plexiglass, as distinctly different signals. This suggests that the applied signal altered its properties substantially as it propagated through the surface of interaction. In summary, our current work shows that it's possible to create embedded haptic waveguides within a 3D printed structure to improve signal propagation and limit attenuation and distortion. As hypothesized, we found that the propagation of vibrotactile signals is highly dependent on the medium of actuation. Given identically applied signals across the frequency bandwidth, which was 80 Hertz to 220 Hertz, we measured significant attenuation within conventional surfaces such as Gorilla Glass, plexiglass, and aluminum over the custom 3D printed ABS material with embedded haptic waveguides. Next step in our research would be to include mediation and isolation in the same waveguide design using constructive wave interference. From our previous censored papers, constructive wave interference, or CWI, is when 2 or more physical actuators generate complementary signals which coalesce into a single output, localized as a virtual exciter. And in our next research, we will investigate how surfaces with embedded haptic waveguides can improve the efficiency of a virtual exciter through CWI. Thank you for attending this online presentation on 3D printed embedded haptic waveguides. And if you have any questions, we'll be happy to answer them now. Thank you.